Hi guys, welcome to the first video on differentiation, where we'll focus on exploring the definition of a derivative. Our goal in this video is to understand what a derivative is, what its formal definition means, and how to use the definition to calculate them. First, I want to talk to you about what a derivative allows us to do, which is that it allows us for an arbitrary function to calculate the slope of the tangent line at any point. The slope, which is also known as the instantaneous rate of change, indicates to us how the function is changing at that point. It's a lot to take in, but the animation which I'm about to show will help you understand it better. This is the graph of sine of x, and the animation shows the tangent line varying for different values of x. I'm going to give you a few seconds to look at this. If I pause the animation and let the x value be pi, then the slope of the tangent line is -1, and this indicates that the curve at x equals pi is decreasing at a rate of 1. If I set the x value to be pi over 2 instead, which is around 1.57, then you could see how the curve is not increasing nor decreasing at the point, and this is indicated by the slope of the tangent line being 0. If I set the x value to be 0, then the slope of the line is 1, and this indicates that the curve is increasing at a rate of 1 at this point. And finally, if I set the x value to be pi over 4, then you can see how the slope of the tangent line is still positive, but it's less than 1. And the slope tells us that even though the curve is still increasing at pi over 4, it's not increasing as quickly as it was at 0. The slope of the tangent line therefore shows at each individual point how the curve varies by showing whether the curve is increasing or decreasing through its sign, and if so, it gives a numerical value to indicate how fast it is doing so. And this is why the slope is called the instantaneous rate of change. And you could think of the slope not only for the tangent line, but also for the curve itself at that point. Each curve has a slope, and the slope of the curve at that point has the same value as the slope of the tangent line to the curve at that point. The difference between a line and a curve is that the slope of the curve varies for different x values, as shown for sine of x, which increases and decreases, while a line always has a constant slope. And differentiation, or finding the derivative, gives you the slope of the tangent line and ultimately the slope of the curve. Our goal will be to find a way to calculate the exact value of a slope through using a derivative. Before we begin doing so, one final note is that the tangent line at a curve may intersect the curve more than once if the curve is not a circle. For instance, the tangent line shown in the right picture intersects the curve 3 times. The goal of the tangent line slope is to indicate how the curve increases or decreases at a particular point through the sign and magnitude of the slope. For instance, you can see how the blue line has a negative slope, and this indicates that at the purple point the red curve is decreasing, and how fast the red curve is decreasing at the purple point is indicated by the magnitude of the slope of the blue line. Notice also that even though the tangent line does intersect with the curve more than once, it does not intersect with the points that are close to or local to the purple point of tangency as shown in green, but rather someplace far away from the purple point. So how do we find the slope of the tangent line? So let's start with a review. So what's the average rate of change of f of x equals x squared from x equal 1 to x equal 3? I'll give you a couple of seconds to try and figure it out. Please pause the video if you need more time. So if I have the points 1, 1 and 3, 9 on the curve y is equal to x squared, then the average rate of change of x squared from x equals 1 to x equals 3 could be found by using the formula for the slope m is equal to y2 minus y1 over x2 minus x1. And this gives us 3 squared minus 1 squared over 2, which is equal to 9 minus 1 over 2, which is equal to 8 over 2, which is equal to 4. However, notice that we found the average rate of change between the 2 points and the slope, or in other words, we found the slope of the secant line of the parabola from x equals 1 to x equals 3. And while we're making good progress by finding the secant line of the curve from x equals 1 to x equals 3, we want to find the tangent line at just x equals 1 to the curve. In order to do so, we're going to move the point 3, 9 closer to 1, 1, and we're going to keep on finding the average rate of change and see how the average rate of change varies through the Desmos animation. The animation shows the slope of the secant line to the parabola as the purple point at 3, 9 moves closer to the 1, 1 point. The green line shows the distance of the x values between the 2 points. The length of this line is also shown in the b-1 cell, while m represents the slope of the secant line and b represents the x value of the purple dot. Now I added a step size to the graph, and I'm going to play the animation again. When I do, I want you to focus on how the slope changes the m value as the purple point moves closer to the black point. 1, 1. Notice that when the 2 points get closer together, the slope seems to approach 2. However, notice that when the x value of the purple dot is actually equal to 1, the slope is still undefined, as there is only 1 point. We always need 2 points to calculate slope. However, if we make the second point very, very close to the first point, then the difference between the 2 points will almost be negligible, causing the slope of the secant line to become the slope of the tangent line, and the average rate of change to become the instantaneous rate of change. Mathematically, we could represent this as a limit, where as the distance between the 2 points go to 0, the secant line slope approaches 2, which is the tangent line slope at the point 1, 1. The slide summarizes what I just mentioned. By using the limiting process to minimize the distance between the points, the slope of the tangent line could be found to be exactly 2, through finding the slope of the secant line and bringing the 2 points closer together. And once again, just as a reminder, remember, we're still using 2 points to calculate the slope of the tangent line. It is just that the second point is so close to the first point that we could find the slope of the tangent line to be exactly 2 at x equals 1. So our second goal is to find the slope of the tangent line for an arbitrary function f at any arbitrary point x, f of x. In other words, we're generalizing what we saw in the previous slide. So we start by having an arbitrary function f, which has 2 points. The first point is defined as x, f of x, and the 2 points are separated by the distance delta x. Therefore, the second point could be written as x plus delta x, f of x plus delta x. Therefore, the average rate of change, or slope of the secant line between the 2 points, could be found by using the formula m is equal to y2 minus y1 over x2 minus x1, as before, and this gives us f of x plus delta x minus f of x over x plus delta x minus x, and we end up with f of the slope of the secant line being f of x plus delta x minus f of x over delta x, and this is known as the difference quotient. However, we want the distance between the 2 points to approach 0, similar to our previous example. This could be done by taking the limit as delta x approaches 0, or in other words, we're minimizing the distance between the 2 points. This gives us an expression for the slope of the tangent line for any arbitrary function at any point, and is the expression that defines the derivative. One minor thing is that different variables could be used, and we'll use h instead of delta x, but besides this, this is the official definition of the derivative, and this will give us the tangent line slope. Let's start by finding the slope of the tangent line to y is equal to x squared at 1, 1. So first, we're going to start with the definition of the derivative from the previous slide. So there's the definition of the derivative, and then we could substitute f of x equals x squared and x equals 1. So from there we see that there's a binomial 1 plus h squared, so we could go expand the binomial. We end up with 1 plus 2 times 1 times h plus h squared minus 1 all over h. And once we combine like terms, we simplify everything, we cancel out the 1's. We end up with the limit as h approaches 0 of 2h plus h squared over h. Notice that I'm still keeping the limit notation. Finally, we could divide by h and plug in h equals 0, so we have the limit as h approaches 0 of 2 plus h, which is equal to 2. And this is just as expected from the previous slides. As the definition of the derivative is a limit, the techniques used to calculate limits, such as rationalization and factoring, will be used, and we'll have more practice next lesson. And this tells us that at x equals 1, the function y is equal x squared is increasing at a rate of 2. And this may be a simple limit compared to the ones you did before, but it shows how to apply the definition of a derivative. So our final goal is to express the derivative as a function. What if I asked you to find the derivative for the same curve y is equal to x squared when x is equal to -3, -1? How about 17.07? It is very monotonous to evaluate the same limit over and over again for different x values. Therefore, rather than outputting a number from the limit each and every time, we can just output a function instead. The function could take in the x values and output the slope of the tangent line for f of x at that point. And this function is known as the derivative of f of x, and one way to notate it is f prime of x as shown. As curves have varying slopes at different points, the outputs of f prime of x varies for different x values. F prime of x depends on the function f of x, and it could change based on what x value the function is. For instance, let us find the derivative of y is equal to x squared and evaluate it at x equals -1, 1, and 3. We're going to do the same things as before, except we do not plug in a certain x value to our definition. Rather, we only plug in f of x, the function, into our definition, and we're going to leave the variable x as it is to represent an arbitrary x value. We're going to do the same thing as previously shown. We're going to expand the binomial x plus h squared to get x squared plus 2xh plus h squared, and then we have minus x squared, so the two x squareds cancel. So we end up with limit as h approaches 0 of 2xh plus h squared over h. We could divide out the h's, and we have the limit as h approaches 0 of 2x plus h. When h is equal to 0, we end up with f prime of x equals 2x. In other words, for any x value you plug in into f prime of x, you'll end up with the slope of the tangent line for x squared at the x value. If I plug in x equals -1, I get f prime of -1 is equal to -2. I get f of 1 equals 2, just as expected from previous slides, and f of 3 is equal to 6. Then what does f prime of -1 mean? Well, it shows that the slope of the tangent line to y equals x squared at x equals -1 is -2, or that the slope of the curve of y equals x squared itself is -2. This means that the curve is decreasing at a rate of 2 at x equals -1. Finally, the derivative also shows that the instantaneous rate of change is -2 at x equals -1. We could also say the same for the other 2 points. So I just want to end by talking about what we'll be doing during the next video. We'll be using the limit definition from what we learned today to calculate derivatives of various types of functions. The techniques for calculating limits, such as rationalizing the denominator or multiplying by the conjugate, will be very useful in computing the limits, as we'll see next time. That's it. See you all next time.